Hi, I'm Gemma, and I'm making this video just to briefly introduce what I've done in my EL6825 final project. All the points are included in my final report, so I won't talk about everything in detail, just a brief introduction. First, I want to talk about the background. The task of semantic segmentation is crucial in computer vision as it involves classifying each pixel of an image into a specific category. This technique has numerous applications, including autonomous driving, urban planning, and scene understanding. In this study, we focus on the cityscapes dataset. It's a large-scale dataset containing diverse urban street scenes. Our goal is to build three popular deep learning models for semantic segmentation: U-Net, SegNet, and DeepLab v3, which is the latest version of DeepLab. Then we compare the performance. By analyzing their strengths and weaknesses, we hope to provide insights into their suitability for various applications. Semantic segmentation of urban scenes is a challenging problem due to the high variability of objects, their appearances, and their spatial relationships. The cityscapes dataset, comprising images from 50 different cities, provides an excellent benchmark for evaluating semantic segmentation algorithms. Our objective is to assess the performance of U-Net, SegNet, and DeepLab v3 on this dataset and identify areas for potential improvements. The three models we're focusing on have been widely used and achieved state-of-the-art performance in various semantic segmentation tasks. The first one is U-Net. It's introduced by Ronnie Berger at 2015. U-Net is an encoder-decoder architecture specifically designed for biomedical image segmentation. The model consists of a contracting path, which works as an encoder, and an expanding path, which works as a decoder, that are connected by skip connections, which help recover spatial information lost during downsampling. U-Net has been widely adopted and adapted for different applications, including semantic segmentation for urban scenes. Next one is SegNet. It's proposed by Badrinarayanan in 2017. SegNet is another encoder-decoder architecture. The key feature of SegNet is its use of pooling indices from the encoder to perform nonlinear upsampling in the decoder, which helps recover detailed spatial information. SegNet has been used for various semantic segmentation tasks, including rope scene understanding and aerial image segmentation. Next one is DeepLab v3. It's developed by Liang-Chi Chen at 2017 and is an advanced semantic segmentation model that employs ITROS convolution and ITROS spatial pyramid pooling to capture multi-scale context. The model also utilizes fully connected conditional random fields to refine segmentation results. DeepLab v3 has demonstrated performance on several challenging datasets, including our dataset. We conducted experiments on the cityscapes dataset using train and validation set. The dataset contains 5,000 high-quality annotated images with 19 semantic classes. We first resized the images to 256 times 512 pixels and normalized them. Then we implemented the three models using TensorFlow and trained them using the same hyperparameters, learning rate of 0.001, batch size of 16, and the LM optimizer. We are also using categorical cross-entropy as loss function. In my implementation of SegNet, the encoding part consists of multiple convolutional and pooling layers that progressively downsample the input image. The decoding part upsamples the features and uses convolutional layers to recover the original image resolution. This symmetric architecture allows the model to learn different scales of features and generate accurate segmentation masks. In my implementation of UNet, I've added skip connections by concatenating the corresponding encoding layers with their decoding counterparts. These connections enable the model to capture more accurate spatial information and help maintain the intricate details of the segmented objects, leading to better segmentation results. In my implementation of DeepLab V3, I have employed depth-wise convolutions for efficient computation and utilized ASPP to capture multi-scale context information. This combination allows the model to efficiently process images with varying scales and object complexities, making it particularly suitable for complex urban scenes like our dataset. Due to time constraints and insufficient computational resources, we only trained one epoch for SegNet, 2 epochs for UNet, and 20 epochs for DeepLab V3. Then we predicted the results on validation set. Here are some results. Based on the results, we can observe that DeepLab V3, having been trained for more epochs, demonstrated the best performance among the 3 models in terms of LU score. The contours of the buildings and the roads could be depicted, although not so distinctly. We can differentiate between trees, pedestrians, and roads to some extent. UNet's performance is almost the same with that of SegNet, even though it's trained for fewer epochs. This could be due to the architecture of UNet, which incorporates skip connections that enable better gradient flow and helping recovering finer details in the output. The performance is poor, which is as expected. We can only differentiate between roads and buildings, but very ambiguously. The performance of SegNet indicated that its architecture might not be as effective for this specific task of dataset. The performance is the worst. We can only segment the image into 3 parts, with one representing the roads, one representing the buildings, and one representing the trees. The last 2 parts mixed together, which makes no sense. Also, we can check these results in my test notebook. Just one sec. Here, I'm not going to run it because it takes some time, like 2 minutes for DeepLab V3 and 12 minutes for SegNet and 30 minutes for UNet. To further improve the performance of these models, future work could explore incorporating additional techniques such as residual connections for SegNet, increasing the depth of UNet length, and experimenting with different numbers of parallel edge flows convolutions in ASPP module to capture a wider range of contextual information for DeepLab V3. Moreover, a more extensive evaluation of these models across different datasets and applications could provide deeper insights into their generalizability and limitations. Overall, our study demonstrates the effectiveness of deep learning-based semantic segmentation models on urban scene understanding and provides valuable insights for practitioners and researchers working in this area. I think that's all for my presentation about my final project. In the end, I would like to express my gratitude to my instructor, Professor Tatia Silva, and T.H. Sun. Thank you for your dedication. I had a really fulfilling semester and learned a lot from this course. Thank you.